This facility requires an industrial footprint of concrete, massive aeration tanks, and millions of dollars in annual maintenance just to keep a city's water clean. Now consider this natural wetland. It filters and purifies water using its own biological processes, performing an identical industrial job entirely for free. In the language of global economics, that $0 price tag creates a blind spot. Because commercial markets rely on prices to signal importance, natural services that don't come with an invoice are often treated as if they have no impact on the bottom line. If we want to protect these ecosystems from being cleared for development, we have to force them into the ledger. We have to give them a mathematical price. To bridge this gap, economists use a specific workaround called the replacement cost method. The logic is straightforward. If an ecosystem suddenly disappeared, what would it actually cost humanity to build a human-made equivalent to take its place? While the formula is simple, applying it to a living landscape requires strict technical discipline. Without a narrow set of rules, the final number can easily lose its connection to economic reality. In the 1990s, the Thailand Forestry Department tried to use this method to protect their coastline. At the time, vast stretches of mangroves were being cleared to make room for the commercial shrimp farming industry. They needed to prove that the natural storm protection these trees provided was more valuable than the short-term profits of the farms. Researchers began with a baseline assumption. A 75-meter-thick mangrove forest provides the same level of coastal protection as a human-made concrete breakwater. At the time, constructing these interlocking concrete breakwaters cost exactly $875 per meter. By multiplying that replacement cost across the total area of the forest, the researchers reached a final valuation. The mangroves were worth roughly $112,000 per hectare. That six-figure number was meant to be a defensive shield for the forest, but an autopsy of the calculation shows it was built on three precarious assumptions. Rule 1: exact equivalence. Researchers assumed a 75-meter mangrove cross-section matched a concrete wall's stopping power perfectly. But forest physics are nonlinear. If 50 meters of forest provides 80% of the protection, that one-to-one comparison falls apart. Then there is Rule 2, least cost. The study used expensive concrete blocks for its math, but it didn't investigate if a cheaper alternative, like a simple sand dune or a wooden weir, could have done the same job for less. If an economist selects an overly expensive replacement for their calculation, they aren't finding the ecosystem's value. They are just inflating a hypothetical bill. Even if the physics and the pricing are perfect, the calculation still faces a final hurdle. Rule 3: the willingness to pay. The researchers never established if the local Thai government or the public actually wanted concrete breakwaters. If a community cannot afford a $112,000 per hectare seawall, then that wall is not a realistic replacement. A valid study establishes this willingness through direct surveys or by looking at nearby communities who have already spent their own tax dollars on similar infrastructure. If a population is unwilling or unable to pay for the human-made substitute, then the cost of that substitute is higher than the value they actually place on the service. This highlights the distinction between a cost and a value. A cost is the objective amount of money required to build a structure. Value is a measurement of what people are actually willing to sacrifice to keep a service. By skipping the question of willingness to pay, the Thailand study didn't find what the mangroves were worth to the people living there. They only found a hypothetical construction budget. Despite these risks of inflation, the replacement cost method is a functional tool for conservationists because it relies on observable market data for infrastructure rather than complex, abstract models. But if we want to successfully defend the natural world in a commercial economy, the math we use to represent it has to be airtight.